So the next speaker is Mary Hall from Utah.
Okay. Hi, I'm Mary Hall. I'm going to talk about integrating data layout into compilers and code generators, and although for the purposes of this workshop, it's going to be about sparse tensors, it's something we've been working on in the context of other data layouts, and we're going to talk about it a little bit more generally, at least at the end. And for the purposes of this talk, this is a set of collaborators and the acknowledgments to the funding agencies. So we all have heard a billion times that data movement is the dominant performance and energy cost in modern systems. And so there should be more of a focus than there is today for compilers and code generators to optimize data movement, along with parallelism, of course, to achieve efficient implementation of computations. So in this talk, we're going to refer to data layout as the physical organization of data in memory. And sometimes it's beneficial for the data layout, the physical data layout to differ from the logical organization that is imposed by the computation. And the example for this workshop is sparse tensors. You only want to represent non-zeros. You don't want to represent a bunch of zero-valued elements that aren't contributing to the computation. And you also want to exploit any sort of structure you might have in the non-zero data. So I'm going to talk about a particular paper for the most part in this talk, but I just want to give you some background. So in the Chill compiler, historically, particularly previous student on Vinkit, we published a bunch of papers where we were adding the sparse polyhedral framework to an existing polyhedral compiler. And we were focused on iterating over a single sparse tensor and doing things like SPMV and being able to show that you could use code transformations to generate both format conversion and high performance implementations of that. So the input is C code and a schedule, and the output is high performance code. So we've seen a lot of advances in state of the art, and I'm going to focus on the Taco compiler and the MLAR sparse dialect, which provide this notion of co-iteration. You have multiple sparse tensors, and you want to iterate over them so that you do a computation only when they have non-zero value. The tensors have non-zero values. And like with these other compilers, today's premise is that the input is an Einstein notation and some sort of layout specification. And in both Taco and MLR sparse dialect, this notion of assigning a dimension of a sparse tensor to the corresponding tensor dimension and generating code based on that has a particular limitation when you don't have a matching the indices to the indices corresponding to the matrix, and in particular block structured tensors, which we're going to come back to at the end. So Tuowen Zhao, as part of his PhD thesis, built a compiler called dlcomp. And so we're going to just kind of walk through what dlcomp does, its code generation strategy, and how it's a little bit different. So we're going to start with a very basic dot product so that that we can fit it on a slide. So the logical dense computation is the sum of the product of two elements of corresponding elements of a vector. And what dlcomp does instead of this dense computation is it's actually going to iterate over one of the data layouts. We'll call it the primary tensor. And it's going to iterate over what we call the physical representation, the actual data layout in memory, just the non-zeros of the first tensor. And then for the secondary, for any secondary input sparse tensor, it's going to do a find operation. It's going to look up that the corresponding element, and it's going to do look up that index using an inverse map that takes you from the index to the physical location in memory. Okay, and then in this compiler, the output tensor is restricted to either be dense or you can infer its size from the input tensors. And this was a paper, this is a reference to a paper that appeared in March. Okay, so this is where a 15-minute talk is very hard to dig into the details, but this is a very high-level summary of what the compiler does. So, so we are representing the computation layout and properties of the layout in the sparse polyhedral framework. And so now we have a mathematical representation that describes the physical layout and its mapping to the iteration space, the logical iteration space. And the sparse polyhedral framework is a polyhedral framework that includes uninterpreted functions for the values you don't know at runtime, the things that give you the mapping, the start of a row, or the, which block you're in, or the mapping from the physical to the logical iteration space. So that's how we're going to represent the problem, and we're describing layouts in the sparse polyhedral framework as well. So we're going to compose that layout with a computation, and in a polyhedral framework, you reason about iteration spaces that describe how you're going to iterate over a loop, and we're going to compose the iteration space of the layout with the iteration space of the loop nest computation, the logical loop nest computation. And when we generate code, we're going to use a mix of polyhedra scanning and code synthesis. So when we want to iterate over a layout, we use polyhedral scanning. When we're doing these lookups of the other tensors, we're going to use code synthesis, and we're going to confirm that based on the constraints that we provide, that we're generating valid code. Okay, so there's your compiler summary. And so let's just kind of walk through this dot product and show you how it's represented and what the generated code looks like. So the physical layout is, in C, it's a length, and that's how many non-zeros there are. And for each non-zero, it has an index and a value. Okay, and so the physical, something, here, let me fix this. Something that I messed up. Okay, so the physical to logical layout mapping says 0 is less than or equal to the indices in the layout of A, is less than A length, and same thing for B. So that's the indices of the physical layout. And then that we're looking for locations where A index PA equals I equals B index PB, which means that they're referring to the same location. We have a mapping property, and this is related to some prior work by our collaborators at University of Arizona, and we're introducing index array properties. So the property of this is basically saying that if my PA value is less than, if one PA value is less than the other PA value, then the indices are also have the same relationship. So it's monotonic, so the indices are sorted. Okay, and so we end up with this co-iteration code, and the two things that are happening, we're going to look at this a little more carefully in the next slide, but the two things that are happening are that we're iterating over the non-zeros in A with a for loop, and we're doing the lookup in B with this while loop, and if we find the same location, then we do the computation. And this is a side-by-side comparison with Taco. Hopefully it still generates this code for this example. And so the difference is that it's a little bit more efficient to do things this way. I mean, this isn't really the important part of this work, but it's a little bit more efficient. In some cases, we see we can generate, we see more of a difference. But so we're looking up a index of A once in the for loop, and then we're searching for B. So we're going to just increment B in the while loop and do the computation when we get the same result. Okay, and so just a few more performance results. This paper has a bunch of comparisons. This is for SPMV. The comparison this is for sparse, I skipped the SPMV. This is for sparse matrix times sparse vector, and we compared with Taco, eigen, and sweet sparse graph laws, and these are all the matrices that we could run in the sweet sparse collection, and the picture shows everything to the right of one is where dlcomp achieved a speed up. And the height of the point is how many of the matrices we saw performance in this range. We did a histogram. So the geometric mean, so we have two different find algorithms that were represented in this paper, a sequential iteration, which you saw in the previous slide, or a hash map, which is much more efficient if you have very, very sparse matrices. And so if you choose between the two, then the speed up is better. But, and speed up over, we're particularly getting a high speed up over eigen. And this is an example comparing against Taco, and it's for things that are very sparse, and the speed ups, that's when the speed ups get significant. And then we also have results on a higher order tensor, and now the performance is comparable, sometimes a little slower than Taco, but then we show that we can parallelize it in the compiler. So current work is looking at other kinds of layouts. This is looking at block compressed sparse row, which is a very standard block layout, and then one that's designed for very sparse blocks, the compressed block compressed sparse row. And when you do the one on the right, you have to look at the bit set and find the next bit, and so the iterator looks very different from doing a polyhedral scan. Okay, so to wrap up, the takeaway message is that a domain-specific system should provide a data layout that minimizes data movement. So it's much more efficient to iterate over data in the order in which it's stored in memory, to whatever extent you can do that, or to operate on blocks of contiguous data. And this should be built into a domain-specific framework, and it goes beyond tensor computations. We've done a lot of work with fine-grained data blocking as well. And it requires a map from the physical to the logical layout, so you can preserve the logical abstraction. And if you can represent that mapping, and you can do some kind of inverse, then you can, always make this work. And it and you can make it integrated with the compiler and code generator. And so we're iterating over elements in the layout to perform a computation that's applied to all elements in the layout, and the code is automatically generated. And so that's it. And I made it in time, I think. 14 minutes. Any questions? Oh, questions at the end. And there's a discussion, right? Okay, great. Thank you.